Okay. Okay, now it works. Okay, so the idea, so you divide your wave function into 3 pieces, but then you have a coupling between different pieces that can be obtained by permutations, but if the particles are different, then you need to solve them separately. Okay. So after we solved this, equation, we can obtain a full wave function by expanding it in this way, and then we solve Schrödinger equation basically for this decomposition coefficients. Unfortunately, you couple different adiabatic potentials, so you call this piece lambda, you call it adiabatic potential, and you couple different adiabatic potentials, and you couple them with p's and q's. So that's a complicated problem. First, you need to find these lambdas, and it's not easy. So we have heard a talk by Kevin Daly last Monday, how to get it with correlated Gaussian approach, but it's complicated, especially when you need to include all these couplings at the end. It's a tough job. But hyperspherical formalism is really useful if you want to derive some simple universal features that arise from long distance behavior of lambda. And for example, for 3D, you can do all the same steps that we did before, and you would end up with this equation. And you can show that Q and P, they decay fast in 3 dimensions. And using only the lowest lambda, we recover Efimov scenario, and this is scaling constant. In 2D, you can prove that the lowest adiabatic curve is larger than -1/4 rho squared at 2-body threshold, so it means that no Efimov effect. Okay? So you see that instead of solving the full equation, we actually end up with really simple one equation. Okay, so now we go to some results. And first for 3 bosons, and first we would like to establish restrictions on potentials for Borromean binding. So what do we know? We know the 2-body problem with potential of negative or non-positive net volume always has a bound state. And we also know that the lowest adiabatic potential in hyperspherical formalism has 3/4 rho squared repulsive core. So what does it mean for a potential? It means that potential should have fine positive net volume if you look for Borromean states, because otherwise you have always 2-body bound state. And also potential should have finite depth. So you cannot have just a bit negative, you cannot have a potential with positive net volume but really small, because otherwise in hyperspherical pictures it's 3/4 rho squared kills a bound state, 3-body bound state. Okay, and unfortunately we can't say a lot more analytically at this point at least, and we decided to collect some numerical examples and some intuition for different potentials, and we decided to make a numerical search for Borromean states. So we use correlated Gaussian approach, which is a variational method, and we use a wave function, variational wave function in this sum, and then we take 3 Gaussians to make a potential. And then we can tune this B1, B2, B3, and this A1 and A2 to actually make many different potentials, many different shapes of potentials, and to see which potentials can provide a Borromean state and what properties this Borromean state have, and to learn something from this numerical search. And what we find that numerical search, in our numerical search, that we don't have Borromean states for potentials without a barrier. So it means that potentials that look like this can provide a Borromean state in our numerical search if they have if they are deep enough at two-body threshold. But if you have a potential without a barrier, then we couldn't find it numerically. It does not mean that it does not you can't have a Borromean state for such potentials, but we couldn't find it numerically. Also in the literature, for different types of potentials, like van der Waals potentials or different potentials without a barrier, kind of atomic type of potentials, nobody could find Borromean states. So hand-waving explanations that two-body state is bound with smaller overall depths of the attractive part, and which leads to small attractive part in the lowest adiabatic potential for three particles. But unfortunately, at this point, we can't give any strict mathematical answers.
So you restrict the set of potentials which you are looking at to this, which have this positive net volume. Right?
Yes.
So the ones which you show, they do not support two-body bounds.
Yeah, these two do not support bounds. And you can assume that this guy has, you would assume that this guy has negative net volume, but because net volume actually need to multiply by R, so contribution at 0 is smaller. Okay.
So in this hand-waving explanation, what is this two-body bound state?
What I'm trying to say is that so we saw that, for example, for attractive potential, you don't have a Borromean state just because two-body state actually binds easily. So it's like any potential, any attractive potential provides a bound state. And what I'm trying, I mean, I don't have a strict mathematical explanation, but at least what we saw, that two-body state still binds too easily if you don't have a barrier. Okay, but yeah, as I said, we don't have a clear answer on this. But then we found some Borromean states for some potentials, and then we have looked for properties, and we found that they are quite similar to three-dimensional cases. So many people investigated Borromean states in 3D, and then for such potentials, we found that the properties are quite similar. So for example, for deep potentials with an outer barrier and without a core, properties actually very similar to a harmonic oscillator described before. So it has large Borromean window, and then the binding engine extent at G2 is of natural order. So if you have a depth of potential gives you natural order and the range gives you natural order, then your three-body state will be of this order. Yeah. And then potentials with a large core and a barrier actually give you much smaller Borromean window, and they have smaller binding engine, large extent. Also, if you evolve, so if you go from in your stance parameter from G2 to G3, the three-body Rotman square radius diverges. It's nothing special, but so it's not confined. Okay, and then we still have plenty of unanswered questions. So first, can we have a Borromean states in a potential without a barrier? So that's one question. And the question that I really would like to answer is it possible to construct a theory with one additional parameter produced by overall features of the potential that will tell if there is a three-body bound state at G2? So you introduce some external kind of universal parameters that will tell you if you can have a Borromean state. Okay, we are running out of time, but still, now I would like to talk about super Efimov states, but now using hyperspherical approach. So what we would like to do, we would like to solve this equation, as I showed before. We would like to solve this equation first, because as we know that for Efimov scenario, you solve this equation, take the lowest lambda, and it's enough to produce a Efimov scenario. And of course, we have some symmetries that we would like to take into account to simplify our calculations. And first we notice that Hamiltonian commutes with the operator of the total angular momentum, and it has this is the total angular momentum in dimensionless units, and this eigenstate of this angular momentum. And we decompose our Faddeev component into this basis, and such that so we decompose in phi x and phi y bases separately, such that they have a total angular momentum as a good quantum number. And what we know that for super Efimov states, m is supposed to be plus minus 1, and then for spinless fermions, L is supposed to be odd, just to satisfy antisymmetrized conditions. Okay, and then we are interested in large distance behavior, because infinitely many states can come only at large distance. So we restrict rho to be very large, larger than any scale in a problem. Yes? Yes. Not the scattering lines. So we consider rho to be large. And for the lowest potential, we need to take only the smallest. So for the lowest potential, we need to take only the smallest L. So here you have infinite sum, and then you can take this infinite sum and put it into your equation, and it will give you infinite amount of couple equations. But we can prove that if you consider only large distance behavior, then you need to take only plus minus 1 L, just because in all other channels, so it means that two particles can approach each other in only plus minus 1 channel, because all other channels are suppressed due to higher partial waves. And this leads to two coupled equations. So 1 and 2, and these are the couplings that come from, so if you use the full wave function, and those are your couplings. And the problem to solve this equation is to establish these couplings. So the way we proceed, we divide our space into two parts. So we divide our angle alpha into two parts, alpha less than some alpha 0, where this potential is non-zero, and alpha larger than alpha 0, and this potential is 0. And then if this potential is 0, we actually end up in equation that do not depend on rho, and it's solved by some polynomials, and then we just match at this angle alpha equal to alpha 0. And in this way we can establish lambda, and I would like to point out to this paper, we are not the only group who worked in hyperspherical approach to understand super Efimov states. It was another paper, and without actually their results, our results would not be correct, and without our results, their results also would not be correct. So that's nice to have another group working on the same problem, and having flow of ideas. Okay, so what we get that the lowest lambda looks like this, and here I write two. So you can decompose this lambda in the series of 1 over log rho, and I write two first terms. And then, so what you do, you now go back to your equations for f, and first you neglect couplings as you did in 3D.
Why do you keep exactly the first two terms?
I will explain. So you need it. So it's like first if you neglect couplings as in 3D, then you end up with this equation. And then in this equation, you actually, if you consider large rho behavior, you can neglect this part, because everything is driven just by this part. And for energy 0, you can actually solve equation. So without these two parts, you can solve the equation. And the solution looks like this. And you see that zero energy solution has infinite amount of oscillations.
I think I may have the same question that Hans-Werner has. In your first equation,
Mhm.
the correction seems to be of the same order as the term that you have just before. Is that a typo?
This one?
Yeah.
But this is smaller.
Small.
Small o, sorry.
That's not order.
No, that's not order. That's small.
Small.
Yeah, sorry, that's mathematical.
So
That
that's
probably.
a number?
No, that means just that all the corrections are smaller than this one.
Or it's a different notation. With a small o, you mean everything that's smaller than this, and if you have a big O, then you mean terms including what you write in the bracket.
It's not so commonly used. It means that they are.
Okay.
So it means that you can neglect these terms.
Okay, so it's the usual thing. Okay, thanks.
Okay. And then, so you solve it for zero energy, and then you see infinite amount of oscillations, which means that this piece provides you infinite amount of bound states. And then you can estimate energy of bound states using either WKB or directly this equation, actually. And you get that the scaling of this bound state looks like this. But it's not the same as in super Efimov scenario, yeah? So,
And what would change if you include the 1 over log square term now? That
Like,
would give you the same result here?
if I include this term, I would have the same scaling, but they will be a bit more bound because you have here negative sign.
And this would not change by including any finite number of terms of higher order in this 1 over log.
It's like it would not be changed because you can show that they're small.
So you made the interpretation, you have an infinite number of wiggles,
Mhm.
and from that you deduce you have an infinite number of bound states.
Yes.
I don't see.
So the idea is the following. So you have an oscillating theorem that tells you that the first state should not have any wiggles. The second state should have one wiggle, and so forth. And if you go to the state, some state, and it's zero state, and it has infinite amount of wiggles, then it means that below the state, you need to have infinitely many bound states.
A scattering state
Yeah.
for some potential that has a finite number of bound states and then a continuum. All these continuum states also have the
Yeah, but for continuum state, it means that below you would have infinitely many continuum states. But here, you say that for energy less than zero,
Oh, okay, the energy is fixed for it.
yes. Okay? Okay, what is going wrong? So it's like we got some scaling, which is not the same in super Efimov scenario. What is going wrong? And for previous slides to be valid, Q and P should be small at large distance. However, when you actually calculate them, they're the same. So it's like the first, the leading order is the same, and it comes with the same number as lambda. Okay? And this means that you cannot neglect couplings, and that's why I include the second term. So, you need to calculate now the second term to actually see what is going on, but it's something that we did not do yet. I mean, we're working on it. It's not that easy to do everything consistently.
In order to understand why you don't need to do this in 3D. In 3D, this would go like 1 over rho squared and no logarithm. And
It's like in 3D, it would go as 1 over 4.
1 over rho 4.
Yes, I believe so. And
You mean the second term.
it's like in 3D, this Q would go as 1 over rho 4 and then larger terms. I guess 1 over rho to the 4.
I think you had something like 1 over rho squared for coupling potentials in one of your previous transparencies, but maybe I confused that.
Okay, we can return to this later. So now what do we want to do next? What we want to calculate this question mark. And if you calculate this question mark and again neglect other couplings, you end up with such an equation. And for this equation you can also solve when energy is 0, and the solution looks like this. And this actually reminds you about Efimov scenario because it has log something, but here it has log, and this means that we require a super Efimov scenario if this question mark is exactly 1 divided by 4, and all other couplings are small, and it's something that we work now. I guess we can show that the couplings, other couplings are small